So, good morning and welcome back to the class for smart materials and structures. Can anyone quickly let me know what was the topic we were dealing in the last class?
Ma'am, yesterday we were discussing about the basic principle of sensor, then type of components that is being used in the mechatronic system, then the working of our transducer, then the different types of sensors. Uh, then we discussed about a linear variable differential transformer, ma'am. Then
Yes,
types of common sensors that is been employed, then
exactly. Then,
actuators, some of the
yes.
working of DC motors and AC motors, ma'am.
Yes. And also, we just had some glimpse related to the conductivity features in semiconductors. So, how it gets enhancement in the conductivity. We also focused on about, if I remember, P type and N type semiconductivity features as per our syllabus, right? Hope you remember those also.
Yes, ma'am.
Yeah. So now further as per your syllabus, you have a version related to the crystallographic planes, its orientation. These are of your basic physics, what you have studied already, but still you have the syllabus related to the crystallographic planes. Why this is basically put forward here in your syllabus is, so when you want to make a device, right, all the concepts, it is very much essential, right from selecting the proper class of smart material, its properties, functionality, design, right? So in which crystallographic plane you will get better enhancement of the results. Suppose if you go for piezo material, if it is of an orthorhombic crystal structure, so across the crystallographic plane, if I give you an example, around 111 plane, you will get the highest piezoelectric charge coefficients. So there the crystallographic planes plays a vital role. So a glimpse of the concept related to those are also being given in your last module related to devices. So it is just nothing but the brushing of the things what you have done already. This is nowhere a new thing what you have to study. You have done right from your 11th, 12th standard related to the lattice structure, the crystallographic planes in your basic physics. So that is the same thing. I'm just focusing on the things which are essential as per your device making. That's it. Just and brush out part of this, right? So you should be knowing exactly the crystallographic points, the directions, and the planes, right? So if you consider this as a single crystal structure, so this will be our X, Y, and Z plane. So the inclination of angle across these three reference planes are referred by the angles associated accordingly. So if it is between Z and Y plane, it is the angle alpha. If it is between Z and X, it is angle beta. And if you have an angle of approach in between X and Y as shown in the diagram here, you'll be having the angle associated, which is nothing but the gamma. Okay, so wherever when you want to synthesize a device, it could be a single crystal device, a polycrystalline material you're using to make an actual dimensioned device. So you should be able to figure out which is the location, which is the direction, which is the plane you're selecting to make that particular device, because orientation of all the ions across that particular plane is very much essential to get the highest properties. So always it is very much necessary to specify the location, the point, the direction, and the plane of an unit cell. So unit cell, it comes into picture for any type of element of the material what you are selecting, right? So every element has its own crystal structure, single unit. So when it comes for the location of the unit cell of a given element, all these parameters plays an vital role. So you need to provide some convention for the unit cell. Suppose if you consider this as an unit, this cube, what you're feeling, looking like, it is a single unit cell structure, right? So it could be always expressed in terms of a three-dimensional object. So in that, you need to show the location where it is placed. So this is the location. Always in normal, when you go for plotting a graph, you take your positive right side to be as our x-axis. But here it is totally reverse, right? So this will be our y, and this will be our z, and this will be our x. Usually this direction we refer to be as z, and this as x, and this as y. But here, don't get confused with respect to the unit cell. This is the location direction what you have to consider, right? So this location will be always represented by the indices. So every crystal structure will be having its own indices, right? So this will be referred to be as A, B, and C. Okay, so you'll be having three indices. So it will be A, B, and C. So accordingly, the angle associated will be alpha, beta, and gamma. What you have to be thorough enough. And later, you should understand about the crystallographic direction. So this crystallographic direction is always a vector quantity. So it will be given in U, V, and W. Suppose if you say it is an crystallographic structure of 0, 0, 0 plane, so then its magnitude is totally like it has a magnitude and direction both. When you speak about the vector, it has both the magnitude and direction. It is not a scalar quantity. If you tell that as a scalar quantity, then it won't show the direction or the location, right? So always the crystal structure with the Miller indices value, what you provide will be a vector quantity. It will be having the magnitude as well as the direction. So you should provide the magnitude. So magnitude will be A, B, and C. How it is located, specifically along Y, Z, and X axis with respect to some angle, alpha, beta, and gamma. So that will show you the location, and the magnitude will be your A, B, and C values. So that you should be very keen and specific. What are the importance of using these parameters related to the crystallographic plane? Okay, so the dimensions, suppose if you consider this as a cube, so this is our unit cell. So every cube or any other solid object, right, it will be, when you assume to be as a three-dimensional system, it will be having length, breadth, and width, right? So that is the magnitude of the unit cell what you are measuring in terms of A, B, and C. Suppose if you just synthesize a small sample of powder and go and do its XRD characterization, right? Or else, yeah. So in that you can identify, if you go and do the analysis of the element, right? So you can in depth identify what are its magnitude, what is the Miller indices. So many softwares are available to do the analysis of the diffraction data. So in that position, so when you do the analysis, so you have a software called foolproof. So in that, if you just select the element and do the peak analysis, it shows the unit cell's crystal structure, what are its values A, B, and C, which is the plane where it has been oriented. So you can identify easily, okay, the material what you have synthesized is having this crystallographic plane. So this is the magnitude A, B, and C. So seeing the magnitude, you can see whether it is in good, yeah, you have a lesser magnitude of the unit cell, whether you need to modify. So many things comes out into picture. To understand into that level, you should be knowing the basic concept of crystallographic points, directions, and plane, right? So I'm just brushing out what you are known already, right? So this is the importance of the cell dimensions A, B, and C. So this provide you the magnitude, and alpha, beta, gamma will provide you the location with respect to our Y, X, and Z plane. Hope the things are fine. Any doubts?
No, ma'am. Understood.
Yeah. So one thing, now you know every crystallographic plane as its magnitude and direction, and hence it is a vector quantity where you need to specify the point, the direction, and the planes, right? So when it comes to the planes, always the planes are associated with Miller indices. So this Miller indices is nothing but the H, K, and L planes, right? So if I don't want to go into depth and go like the crystal structure analysis and tell you which is H, K, and L plane, all those are not there in your syllabus. Only keep, you can go through your basic physics books if you have any doubts still. But I'm just showing you the main things related to the help of making a devices. Okay. So here, all the plane will pass through the origin. It is not like the plane will be, the origin will be here and you will be having the unit cell between the Z and Y. No, so you have one plane, two plane, three planes, right? So all these planes will pass through the origin. So origin is here located nearly somewhere here. Okay, so it will pass through the center. That is the thing what you have to understand when you try to draw an unit structure. How you have to draw? You should draw in such a way that it all the planes will pass through the origin where you have the inclination of z, x, and y plane. So that you have to keep in mind. And then you will provide what is the length of each planar intercept. So every plane has been intercepted at some particular value, right? So this distance, and this distance. So you'll provide the value of length, width, and breadth. Okay, so that is nothing but the lattice parameters A, B, and C. And to identify the Miller indices, we usually take the reciprocal value of the lattice parameters. So lattice parameters are A, B, and C. It provides the unit cell dimensions. So if you take the reciprocal of it, so then you get the Miller indices values. Okay, so this is the thing how you can evaluate the values of Miller indices. Suppose if you go to an image over here, right? So this is just taken from the book. The author is Callister for material science. So here, if you can see that this is an crystallographic plane of 0, 0, 1 plane, means H, K, and L. H plane is 0, K plane is 0, only L plane. So this is the top plane, which is 0, 0, 1 plane. It is interfaced to the origin at point O, right? So this is the origin. So every plane passes through the intersection of the y, z, and x. So this plane is interfaced through the origin O. So this is what you have to tell. So now you have the inclination of 1, 1, 0 plane. So this is the most beautiful plane which yields with good amount of functional properties in many materials. Especially if you go with piezo, 110 and 111 plane will yield you the best piezoelectric charge coefficients. Okay, so both 110 and 111 plane are orthorhombic crystal structures. So if you go for that, you can see that 110 plane. This is the 110 plane. So all the 110 plane is again interfaced to the origin at the point O. It is not like you will be locating the plane without interface to the origin. It has to interface to the origin, right? And other plane you have here again 0, 0, 1. So in this direction, wherever you can have a plane, so everything will be of the same value. If you go with the inclination, then it will be like 110 plane. So all the parallel planes what you are drawn here, it will be of 0, 0, 1 plane only. Even this is also interface to 0 origin. Even this is also interface to the origin. So this is how you put forward. 0, 0, 1 plane yields the best result for some of the class of smart materials. Okay, but 110 and 11 plane, what I'm telling you, this is mainly for piezo. So for whenever you tell 110 plane, you will be having the inclination of the crystal structure in this way, but still it will be interfaced at origin. Suppose if you need 111, means you have a change of crystal structure from orthorhombic to tetrahedron. So in that case, the shape of the plane gets changed. Here it was like an parallelogram. So now there is a change of phase from orthorhombic to tetrahedron, and hence the change of the plane or the shape of the plane also gets changed. So this is the plane what we usually represent for 111. So these are the 111 planes. So any number of planes you draw at equal distance. So all these planes will be interfaced across the origin through which you have your y, z, and x axis. So these are all other equivalent planes. Wherever you take, you will yield with the same HKL values. Okay, so here also you have drawn 110 plane. Further, if you draw any 110 plane, you'll be having the same equivalent planes. Okay, so that is the beauty of drawing the crystallographic planes. It comes only with the experience. You should understand the basic and then you should try to draw the crystallographic planes. And if you try to do the polling along the crystallographic plane of 110 and 111, the maximum functional properties you will usually come into picture in case of smart materials. For that, you should see that the ions of the crystal structure are oriented along the direction of 110 plane. Suppose you have made a suppose transducer made up of piezo, right? So to figure out what are its specification, what is the highest value it can yield. So then in the specification they mention that this is the results you get when you have the polling with respect to 110 plane. Means to say that the people who do the packaging and the manufacturing of the transducer, so they are very keen in focusing the properties which are obtained across 110 plane. Suppose if you have a transducer for the piezoelectric polling which is done across 111 plane, still you will be having a better good results. So it mainly depends upon the orientation of the ions across which crystallographic planes. Hence, crystallographic plane plays a really vital role. Even in MEMS, I told for the substrates. So whether it is in which crystallographic plane. So based on that, again the properties of the devices vary. I told it will vary if it is an anisotropic material. It doesn't vary if it is an isotropic material. That also I told in MEMS chapter. So please remember each and every key points and the thumb rules given. So that remains unchanged. Concepts should be in your head and you should write on the paper by your own. So that will provide the concepts in your head for lifelong. So this is how you need to study. So these are the importance of crystallographic planes. Any doubts associated with this?
No, ma'am.
Hope you people remember your basic physics, what you have done in your 11th, 12th. Even in engineering, I think in first year you had physics, right?
Yes, ma'am.
Yeah, all those are really helpful in your future and in your every day-to-day activities also. Without physics, there is no engineering. So always be strong with physics.
Yes, ma'am.
Basic physics, mathematics is very important. Okay, so I told you the reciprocal of the unit cell values will yield you with the Miller indices. So that's what being written over here. So if you want to focus on Miller indices exactly, so the reciprocal of all the three axial intercepts for a plane will yield you with the values. So if you need to identify how does it work, everything, so even you can try to figure out an algorithm, write the values of A, B, C for each unit cell, take the reciprocals exactly where it is intercepting. So suppose if this is the plane, okay, of 001. So you should see that where these planes are intercepting the X, the Y and Z axis. So that will be the values of your A, B and C. So this will be the dimensions of the unit cell. So with respect to the dimension of the unit cell, you will take the reciprocal of it and then figure out the HKL plane. Okay, so which is nothing but the Miller indices values. So for you to make clear, I've just given some informations from the basic. Okay, so again, these are the crystallographic planes. So what you are getting, so this is for 100 and this is for 110. So whenever you have 110 plane, you will be having an inclined plane. By looking into the plane only, you can tell that it is 110 plane. Okay, so here if you see, so the intercept value for A, so this is A and this is B and this is C. Okay, so it is marked on this is X, Y and Z. The unit cell always looks like a cube. So the cube is placed with respect to our reference planes and it starts from the center of the reference plane. So this is the center. So from here, the magnitude of the value of A, you should measure from the center to the point where it is intercepting at x-axis. So that will be exactly A. So you will write it as value 1, right? And then B. So from the center towards Y, where it is intercepting y-axis, it is intercepting at this particular point. So this will be our B. And this unit measurement is termed to be as 1. So you are writing it as 1. Okay. And now from the center towards Z axis where it has been intercepting is the value C. And suppose it is measured to be as infinite. So then it is like infinity what you write. Okay. So like it is more than 1 unit. If it is more than 1, you will claim to be as infinity. So then it is like writing infinity. So to find out the Miller indices or HKL plane, What's the funda is you need to take the reciprocal of it. So when you take the reciprocal, the value what you had for A, B and C will be put into the denominator. So it is 1 by 1 here, again 1 by 1 here, and 1 upon infinity. Due to 1 upon infinity, the last plane will be termed to be 0, wherein the H and K plane will be as 1 and 1. And hence the Miller indices for this particular unit cell will be 1, 1, 0 plane. So this is an example how to figure out the Miller indices. Okay. So this is C. So from here till here is C, but your plane is having from here till here for 110 plane. It won't touch this point basically. And hence we put on here as infinity. Okay. And now similarly, this is a Miller indices calculation for 100 plane, right? So you can see that from the center to A, it is not 1 unit exactly half, so you're writing 1 by 2. And now when you go for B, so from here till here, it is having the interception across y-axis, but it is not being met at all. Your plane of 100 is here, and hence in place of B, you don't blindly put on as 1, it will be infinity, right? And again, C value from here till here you are knowing, but always we need to measure from the center to the point where it is touching our z-axis. So in 110 plane, this plane is not touching at all z-axis, and hence it will be infinity, right? So after this, you will take the reciprocal of it. So 1 by 2, 1 by infinity, and 1 by infinity, right? So then it will be like 2, 0, 0, right? So then this is a reduction part which comes into picture. So when you simplify it, so finally this will be the Miller indices value what you mention it. Okay, so this is how you calculate the Miller indices value with respect to the given crystallographic planes, and across 1, 1, 0, 1, 1, 1 plane you will yield the maximum results. So I have just given a small example for you all to calculate the crystallographic plane that you can draw and calculate later also. It is for your understanding. Okay, so I have just taken an example of iron foil, which has been used for an catalyst for some particular synthesis of the material, right? So the crystal structure of the iron foil is as shown here. And if you just take 4 atoms here associated, so then you can see the gap between the 4 atoms. So this gap A is been provided by 4 root 3 by 3 into R, where R will be the radius of iron. Okay, so every iron molecule. So it is 0.1241 nanometer. Remember, it won't be even in microns, it will be in nanometer. So if you substitute and calculate, you can identify what is the planar density of iron. Usually when you have good number of atoms compacted together, so then you say that that particular atom, your solid structure, BCC structure, so is of a good density value. So it is of this much value, they figure out chemically. So how will they figure out? They figure out with the help of taking few atoms or molecules together into an unit cell. So this is a huge solid BCC structure. In that, if you consider a single unit cell in the sense, this is a diagram, what you're seeing is a single unit cell. The same single unit cell we used here to refer our HKL planes. Okay, so here one atom will be there, here 1, 1, 1, 1, 1, 1 and 1. And in between the atoms, you'll be having some spacing. Okay, so that also is being calculated by this formula. So how many repeated units you have in a single unit cell? So that is being given. So with the help of this, you can check what is the density of the given BCC structure, and also you can evaluate the planar density for the given unit cell. So this is for your understanding, and this was for 100 plane. So 100 plane, always it looks like a cube. By seeing this crystal structure, the unit cell, you can identify which plane it is. But if you go for 111 plane, it is always inclined in position. Okay, so it looks like a triangle here. So even in this, you will use the formulas to calculate the planar density. This is for your understanding. I don't want to go in depth. So in your syllabus, you have mainly crystallographic planes, directions, and how you determine it. So that much I have done it already, right? So related to planar density, just for your curiosity, I have given some information. You can go through it. And if they ask anything related to single and polycrystalline material, you should be able to tell in. All the smart materials could be synthesized for a single crystalline material and even for polycrystalline material as per the requirement and for what devices you're basically focusing on. So you should be knowing the difference between a single crystal structure and a polycrystal structure. In polycrystal structure, you'll be having more than one unit cell. So n number of crystallographic planes you can show. So as I explained you, right? So you can have more than one unit cell. So it is a polycrystalline material. If it is a single structure, means you have a single unit cell. You cannot claim that as a polycrystalline material, right? So you should be able to understand the things. So in a single crystal material, what happens is the periodic and the repeated arrangement of the atoms will be perfect. So here, see, you have the periodic repeated arrangement of the atoms. You have n number of atoms and it will be periodically arranged and the gap between each will be the same. You won't be having any variations. Okay, so this is the main importance of a single crystal material. So it is termed to be as an perfect material. So wherein when you go for a polycrystalline material, on the other hand, you'll be having n number of grains. The orientation of the grains will be in different location. You'll be having different grain boundaries. You can see here, right? So here the allocation of the atoms are in one order, right? So wherein if you go here for the green color, you can see that the arrangement of the atoms are in an inclined position and you have the grain boundaries in a different inclined angle, right? So this is the variation and abnormalities what you see in polycrystalline material. So you'll be having different crystallographic orientations. You can have like 111 plane, 100 plane, 110 plane as per the orientations you are getting. So in case of a polycrystalline material, you can get all the type of crystallographic planes because it is a polycrystalline material. You can change from orthorhombic to tetrahedron, from tetrahedron to rhombohedron, so whatsoever. So this change of plane takes place when you subject the given material to some heat treatment or annealing or calcination process whatsoever. So all these type of specifications, tailoring the material is possible with respect to polycrystalline material because it has different directions associated with the grain boundary. But that is not the case with single crystal. In single crystal, every atoms will be arranged perfectly with specific spacing, right? If it is an 110 plane, it will be the same throughout. You cannot have any other diversions. So the properties what you get for an piezoelectric single crystal will be different, and the properties what you get, the functional properties for a polycrystalline piezoelectric material will be different. So this is a difference what you get even in the devices when you focus on either sensors or actuators. It is made up of polycrystalline material and the functional properties, the specifications of it will be totally different. And if you're going for a single crystal, then its functional properties will be different. So as per the requirement, you can select which type of crystal structure you need, whether it is a single crystal or a polycrystalline material. So you should be able to think over like what is the importance of a single crystal and a polycrystalline material. So how you can tailor the properties of the material to get the required functional properties. This is very important aspect what you have to understand related to the module 5. Any doubts associated with this? Is it clear enough?
Yes.
Okay. Any doubts, please kindly let me know. So now you know when crystal is been told, it could be a single crystal or a polycrystalline material. In both the crystals, you will be having the crystallographic planes. You know how to evaluate the values of A, B, C, which are the magnitude of the unit cell, and how to locate its direction. Also, you know, and basically they are the vector quantities and not the scalar, and hence it will be having both the magnitude and direction. You need to provide the magnitude of the unit cell, which are A, B, and C, and the Miller indices values, which yield you with the direction, which is nothing but our H, K, and L plane. So this basic thing related to crystal plane is to be understood by you very clearly. Right? So suppose if you use these crystals for any building block, so it varies as per the applications, which are the crystal properties is needed. Okay, so here if you just take an this is an just figure to show you a turbine blade. So here this turbine blade is made up of single crystal. Okay, so the crystal, which is a single crystal which has been used to make a turbine blade. So they claim that it is a diamond, which is a single crystal which has been used. Okay, so this was the claim done by the author Callister in its material science book, right? So similarly, some people have yielded the crystal properties of quartz. So quartz is the naturally available material which is having the functionality of an piezo material. So this is the this is a crystal property related to the atomic structure of the quartz, right? So this is just to make you understand the difference between the atomic structure and a single crystal. So nothing much to worry about. And sometimes the crystals what you use could be like polycrystalline, I told. So this polycrystalline will be having like more number of crystals which are bounded together, which will be having different grain boundaries. So here it is not arranged. If you look at this diagram, you have n number of atoms here, molecules, which are arranged in different directions. It will be having different grain boundaries, and easily you can have different uh, HKL planes, right? So it will be easy to get the required functionality by getting pulled of the ions in the required plane. So this is very much helpful if you are going to tailor an polycrystalline material than that of a single crystal. And hence you should just know the difference between the single and the polycrystal. So what happens here? In single crystals, what happens is the properties always vary with respect to the direction. So you are keen with the specific direction. It will be having one HKL plane, and it is a single unit cell which is neatly packed, and it has equal distance in between the atoms. So that distance can also be figured out. So in that case, the properties what you evaluate, it could be like a shape memory alloy, it has its own functional properties. Piezo material, it will be having its own functional material. Self-healing material, it will be having its own functional properties. So all these properties will vary with respect to the direction. Okay, and this will happen if it is an anisotropic material. Please remember, if it is an isotropic material, what you are using, then the property of it will not vary in any case with respect to the direction. Okay, if it is an anisotropic, so then it keeps on varying. So that you have to understand. And similarly, if it is a polycrystalline material, what happens? Properties can or it may not vary with the direction. Okay, so because here the grains are arranged randomly, it depends upon the grain boundaries. Okay, so if it is arranged randomly and oriented properly, so even if it is an isotropic material, then all the properties of the smart materials will not vary. If it is not isotropic, if it is an anisotropic material, then it may result in varying. So this is a difference what you have to understand. So in single crystal, the properties varies if it is anisotropic. And here it may or may not vary, right? If the grains are randomly oriented. So even with this, if the materials are isotropic, so then it will not vary to a very larger extent. Abnormal variation will occur if it is an anisotropic material. So these things you have to be aware of. So after this, I hope the topic of crystallographic plane, its direction, magnitude, value, everything is clear. Any doubt associated with this and the difference between the crystal and the polycrystalline material? Any doubt?
No, ma'am, understood.
Okay. So then the next part in your syllabus will speak about the stress strain relationship. So the stress strain relationship right from your first year you're studying about this, right? So you have to focus and tell how to relate and relation between the stress and a strain, right? So I'm just brushing out the basic things what you have understood already, which is very much essential to our device making. I'm just taking that part. Okay, so thus when we speak about the stress, when some load is subjected, yeah, force, yeah, pressure, so there is some stress induced in the body. It depends upon which type of stress it is coming into picture. If you're applying a tensile force, then the stress induced in the body is the tensile stress. If you're subjecting a compressive force, then the stress which is induced in the body is nothing but the compression type of stress which is coming across. So the body could be anything. I am here just showing a rod. So if you just take a cross section of the rod, then you can analyze what is the tensile stress which has been depicted in this cylinder rod, right? And if you subject a compressive force, what is the compression stress which is coming into picture, right? So you should be able to evaluate the stresses. And these are called as normal stresses because the stress will be acting along the axial direction. So if you want to figure out the axial stress, because you are applying the force in the axial direction. So axial stress will be equal to the force what you have subjected divided by the cross-sectional area what you are referring. So if you see here the rod, so this is a cross-sectional area which is represented by A. So the axial stress will be equal to the force which has been subjected, which is F upon the cross-sectional area A. Okay, so always the force what you apply should be perpendicular to the cross-sectional area what you are referring. So kindly do remember that one. You cannot blindly apply force in any inclined directions. It should be always perpendicular to the cross-sectional area. So that one thumb rule you should be aware enough. So in this scenario, the regular normal stress, yeah, axial stress, what we usually calculate will be nothing but our force upon the cross-sectional area. So you are aware. Just a second. हेलो, क्लास में हो? थोड़ी देर में फोन करता हूँ. So when it comes for the normal strain, so when a stress has been induced, so what happens that obviously the strain will be generated due to the deformation, right? So now you should also figure out the normal strain. So the normal strain will be depending upon the stress which has been applied. So there'll be change in the length or the dimension of the given object. So you'll take the ratio of change of length to the original length. So that will provide you the strain. So this delta L will show you what is the change you are getting. Suppose you have subjected a tensile type of force, so then you can observe an elongation in the given rod. So this is the extra length what the object has moved in. So this is the change in length what you are getting, and L naught will be the regular length of the rod. So change in length to the original length, delta L upon L naught will yield you the strain. Okay, so once you are thorough with this, you should also be able to figure out the Poisson ratio, right? So the change in the strain along X to the Z direction here, or the strain along the Y direction to the strain along the Z direction will yield as the Poisson's ratio, which is nothing but mu. So as shown in the diagram over here. So this is for your basic thing. Mainly you need to relate an equation between the stress and the strain. And also for going to a strain relationship, you should also consider, like if you're applying a shear force, so then due to the shear force, the shear stress comes into picture apart from the normal stress. So then you should be able to calculate what is the shear stress. It is usually represented by 2. So it is nothing but the force, the shear force what you are applying divided by the cross sectional, the actual area of the given object. So which is nothing but A naught, right? So this is how you calculate the shear stress. And apart from that, when you have a shear stress, you should figure out what is the shear strain also. So shear strain will be associated with the inclination of the angle theta due to the shear mode, the variation or the deformation what you get in the body. So that is nothing but our tan theta. So that you can express as change in x upon the actual length of the given device. So this is the relation what you have to get for shear stress and the shear strain. And apart from that, you may have an uniaxial test, right? So based on that also you can figure out the stress strain relationship. The same thing, the tensile testing what we told related to that. So now I hope the things related to stress strain and shear stress and shear strain is clear enough. Any doubts?
No, ma'am, understood.
If it is clear, then we'll just go for stress strain curves. So if you just go through the stress strain curves, this curve will be different for different material. Here I've just shown a graph of stress versus strain for concrete, cast iron and mild steel. So you can see the variation in stress and strain. In case of mild steel, you can see the yield point and then it has moved to the plasticity range, right? So wherein for cast iron it is different and concrete it is varying linearly. So by looking into the diagram you can tell what has been happening. Suppose the given material is a pure ductile one. So then you can exhibit the actual trend of the stress strain curves. So how the variation will happen so that you can able to identify. You have in your syllabus the stress strain relationship. So even though you have studied already, so you need to mention and explain, right? So here you can see the variation of the stress and strain. So you take stress along y-axis and strain along x-axis. Okay. So the stress and strain, you plot the values. So when you observe the graph over here, so you can see this point from here till here, it is the elastic region. So any deformation what you get, it can come back to its original position. So wherein when it crosses this yield stress point, right, it moves on into the plasticity. So here once it has come to the plasticity, it cannot get back to its original position. So you'll be having an elastic region and a plastic region. In between you will be having the yield stress. So this is the ultimate stress value. Okay, so until here the stress will be proportional to the strain and then it varies as per the behavior of the material, right? So in this you will be having again 3 sections. One is the yielding, the strain hardening, and this is the necking part. Once the necking part has been crossed, the material can fracture, right? So this is the ultimate bearing capacity. So it can wait until the necking region of the stress. So this is the ultimate stress. So this is the strain hardening, almost near to the saturation, and this is the stress associated with yielding stress is nothing but your yielding part. Okay, so you have 3 sections in the plastic behavior of any material. So if you have selected a material to make a device, and if you have the specifications of that material right from its physical properties and its melting property and also the stress strain behavior, so you can understand which is the maximum upper limit within which the material could be safe and when the material could be fractured if you go into an device type of thing. So to understand each and every value, it is necessary to analyze each and every specific properties of the material what you are selecting for device making. Why they are putting all these is when you want to make a device, either a sensor or an actuator, we have covered the device part, but in the background all these parameters related to material plays a very vital role, right from your Miller indices, unit cell, the crystallographic plane what you have studied, the amount of stress and strain which has been induced, and the stress and strain of the stress and strain curve of a particular material, everything will play a vital role. If you have a strong background and analysis of this before going into the device will never fail in a short period of time. It will be having a very high reliability and a good market with a long life. Okay, so and hence doing this background study is very much essential. This is the need why they have put forward all these things together into the module 5 with respect to devices, right? So this is the importance why you need to study all these. So I have just given an example for an brittle material. We just spoke about the stress strain curve for a ductile material, where you will be having the elastic and the plastic region, where you can study the subsection of the plastic behavior of a material as well. So this holds good only if the material what you have selected is a ductile one. If it is a brittle like ceramics, the stress and the strain will vary linearly, right? So this is how you have to understand. And this is again one more low carbon steel. So this also shows a regular stress strain graph right from the ultimate strength to the necking region, as I explained in the previous sketch. So this is about the stress strain curve. So how and where you can understand the variations which is coming into. And specifically, if you need the proportional limit, the elastic limit, the yield point, so you can measure, right, with respect to these values. So this is just to show how to get the values of proportional limit, elastic limit, yield point, the yield strength, and the ultimate strength of the given material. It could, and this values will be different for different material. For mild steel it will be different. If you go on with some other low carbon steel, that will be different, right? If you go for any other smart materials, then the properties of it will vary accordingly. So this thing you have to understand in mind. And this is the same thing with another example to show the variation from elastic region to the plastic region. So this is the neck region where the failure occurs, means the fracture will come into picture. So this is the yield point until which the stress and strain vary linearly, right? Then the plastic region comes into the picture. So this is the true stress and the strain usually comes into in the ductile material. So just to make you understand about it, this was been given. And then actually you need to come for the stress strain relationship, right? The stress strain relationship you have studied already. You know what you mean by Hooke's law, right? So based on the Hooke's law, you can tell that the stress is proportional to the strain. I mean, if you want to remove that proportionality, you should show the value of proportionality, which is nothing but Young's modulus. So Young's modulus will be equal to stress upon strain, right? Suppose if you're focusing on the shear stress, shear force, then the shear modulus comes into the picture, right? So you hear the same thing, the stress and strain will be replaced by the shear stress and the shear strain, which is represented by tau and gamma. So shear stress will be proportional to the shear strain. If you want to remove the proportionality thing, you need to add on one constant, which will be nothing but the shear modulus. So shear modulus will be represented by the letter G. So this is the stress strain relationship, what you should be familiar enough. And suppose if the given material is subjected to thermal treatment, then it will result in inducing some thermal strains, right? So if you have the thermal strains, so then you should add on the thermal associated strain also, right? So it will be a combination of stress due to temperature variant and the stress which is coming due to the subjection of the other forces. So that is related to the thermal strain. They have just asked you the stress strain relationship in your syllabus. So for that, what you have to tell us, you should speak about the importance of the stress and the strain. How does the stress and strain vary? when you have a tensile force, when you have a compressive force, and when you have a shear force. Okay, so you will get different equations for stress and strain. So then you can figure out and draw a graph and show how a stress strain curve will vary. You can explain all the regions, the elastic region and the plastic region and the subsections of the plastic region, which are the different limits, what you can plot on the graph. And also you can explain for a brittle material how the stress strain curve will vary. Okay, so after that you can just draw the graph and show how to evaluate these proportionality limits related to yield strength, yield point, elastic limit, and ultimate strength. And then just come back, define Hooke's law where stress is proportional to strain and show the relationship and what does E stands for, and just explain the shear modulus related to the shear stress and shear strain. So this will complete with the stress strain relationship concept which has been asked in either examination or internals. This thermal strain I have just given you for your information. So this was for uniaxial. Suppose if you need for biaxial state static analysis, so then you have to take care of few parameters. So that I will explain it in the next class. So any doubts related to the crystallographic plane, the stress strain relationships, what we dealt in today's class?
No, ma'am. Understood.
Yeah, Mohan Ambal, you can let me know what you understood in today's class as a part of your quiz.
I understood like for making a smart device, like
Mm-hmm.
it's very necessary to specify the particular point of the direction that,
Mm-hmm.
and we studied about that Miller indices, crystallographic
Yeah.
dynamics,
Mm-hmm.
then planar. We made deep study on crystal of building blocks, Gaussian
Yeah.
method, affine late, single crystal, for quartz,
Mm-hmm.
tensor
Okay.
strain relationship.
Yes. Good. Next, Danush.
Yes, ma'am.
What's the importance of an single crystal and polycrystalline material? When and how it is needed to be used? Any idea you learnt on it? I didn't get a reply from your end.
Ma'am, the voice is little breaking, ma'am.
My voice was audible until now.
My voice, ma'am.
Your voice, I can hear you. Mithun, you're there? Hello. Again, something happened.
Yes, ma'am.
Yeah. So, how was the class today?
Fine, ma'am.
What did you understand from today's class?
Relationship between the stress strain curve,
Yes, what is its
crystallographic lines.
importance? Why it is essential to study stress strain relationship, Mithun? What is the need of studying stress strain relationships? Sandesh? Srinidhi?
Yes, ma'am.
Yeah, can you just tell me why it is needed to study stress strain relationship?
Ma'am, for different material, there is different properties. Like
Yes.
for minefield and cast iron, there is so much of difference in stress strain curves.
Mm,
To
yes,
understand that at what point the material can handle the load.
exactly.
So that's
So
it.
without knowing blindly, we cannot proceed further for device making, because once the device is done, it will be into the market, into the hands of customer. You cannot blindly give anything without testing its performance. So to know the performance, you should know all the material properties of material what you are selecting, which is the ultimate worst case until where it gets fractured. So for all that, it is very much essential to know the importance of stress strain. So that is the reason they have put this concept in your module 5. Okay. Yeah. So I think it is 10:33. Kindly everyone write your name and USN in the chat room. Danush?
Yes, ma'am.
No,
Sorry, ma'am.
until
There was
you
a little network error here, ma'am.
answer, I
Let
won't
me.
give you that attendance. Mithun?
Yes, ma'am.
Mohanambal? Sandesh?
Yes, ma'am.
Srinidhi? Srinidhi, I think you're there. You answered me also.
Yes, ma'am.
Yeah. Sukrut
Yes, ma'am.
and Harsha.
Yes, ma'am.
Yeah, so everyone kindly type your name and USN in the chat room. So we'll meet again in the next class. I think tomorrow we have second hour. So until then, please take care and have a nice day. Don't forget to write your name and USN in the chat room. Anyone have missed out? Yeah, all have written. Fine then. Take care. Have a nice day. Bye bye.
Thank you, ma'am.
Yeah. Thank you.
Thank you,
Yeah,
ma'am.
yeah.